Good day, everyone. Now we will start with the derivation of unipolar rectangular wave, starting with the exponential Fourier series. Given this range, we are going to use the general formula for exponential Fourier series, wherein we will now substitute the important values used in deriving rectangular wave. And based on the range presented earlier, it is ranging from -t/2 to t/2. Now, using some substitution, in order to simplify the solution in deriving the formula, we are simply substituting the values, and this will result into this. Now, based on this formula, we are letting k omega naught t/2 is equals to x, and applying Euler's relation, wherein e raised to ix equals to cosine of x plus I sine x, we are going to result in this equation. And applying sampling function to this equation, we are going to result into this equation, wherein we will simplify this equation. This will simply be cancelled, and also this one. So the final equation of rectangular waveform in unipolar form using exponential Fourier series equals to c sub k is equals to tx naught over t naught sine ct sub k pi over t naught. Now, applying some substitution to some important values, this is the final equation to be used in order to derive the waveform using MatCAD. So this is the exponential rectangular wave. Now we proceed to the next Fourier series, which is the trigonometric Fourier series. So using the general formula, we will apply the given range earlier. So ranging from -t/2 to t/2, and applying simple integration rules, so we will let t equals to t/2 and -t/2. And this will result to a naught equals tx naught over t naught. Next is the c sub k, which is equals to a sub k plus j times b sub k over 2. And since rectangular wave is an even function, b sub k is equals to 0. And now a sub k is equals to 2 times c sub k. Therefore, a sub k is equals to 2tx naught over t naught, sine c times tk pi over t naught. Assigning some values to the formula using this final formula, we are going to arrive in this waveform using the trigonometric Fourier series. Lastly is the derivation using combined trigonometric Fourier series using this general formula. And given that c sub naught is equals to x naught t over t naught, and c sub k is equals to square root of a sub k squared plus b sub k squared, and substituting the values given, wherein it was solved earlier in the trigonometric Fourier series, c sub k is equals to t x naught over t naught sine c times tk pi over t naught squared plus 0. Now, solving for theta k, it is equals to negative arctan b of k over a sub n. Since b sub k is equals to 0, therefore the angle is 0. Now this is the final derived formula using combined trigonometric series, and same with the other rectangular formulas. We're going to use some substitution of important values, and this is the derived waveform. Now using the combined trigonometric Fourier series of rectangular wave, which is f of t is equals to tx naught over t naught plus summation of n, wherein k equals 1, times the quantity of 2tx naught over t naught sine c times tk pi over t naught cosine k times 2 pi over t naught times t. We arrive in these waveforms. First is the time reversal, wherein it was shown in the graph that the time decreases. Next is time shifting, wherein f of t minus 0.5 affected the waveform of the derived rectangular form. Next is amplitude scaling, wherein 0.5 times f of t, it affected the amplitude of the rectangular waveform by 0.5. Next is time scaling, wherein f of 0.5t is affected the time of the waveform by 0.5. Next is amplitude reversal, wherein negative f of t, basically the waveform reversed, is the inverse of the original waveform. And lastly, the amplitude shifting, wherein f of t plus 0.5, the amplitude increased by 0.5. Lastly, we also derived the RMS value of unipolar rectangular wave, wherein VRMS equals to square root of 1 over t, integral of 0 to t, x of t squared, dt, wherein it ranges from 0 to t over 2, and applying integration. Therefore, our formula for VRMS equals to x naught times square root of 1 over t naught times t over 2. Now we proceed to the simulation of the unipolar rectangular waveform. And for this simulation, I specifically used the proto simulator. And basically, this is the circuit that I used in order to generate the waveform of the unipolar rectangular wave. And as we can see, the main components of this circuit are 555 timer, 330 ohm resistor, 10K ohm resistor, and 10 microfarad capacitor. And now, we will basically run the simulator and let us see the results. So this is the generated waveform using this circuit, adjusting its time and the voltage. And this is the expected output when it comes to the actual simulation of the unipolar waveform. Now we proceed to the actual simulation of the rectangular waveform, and as shown in this picture, it shows the setup used in order to generate the waveform, wherein it includes the circuit used and the digital oscilloscope. Now, this is the circuit used in order to generate the waveform, wherein it was based on the simulation that was made in the simulator using Protos. And this was the result in the derivation of the unipolar rectangular waveform, wherein it also shows some of the important values, such as maximum and minimum voltage, and the duty cycle, and the RMS values, and other important values such as frequency. And next, this shows the FFT of the waveform. So these are the values. Thank you for watching.